Okay, so let's take a look at exam 3. Where's my mouse? There it is. Alright, so for number 1, we want to find the geometric angle of these two vectors, and we want exact values. So, in order to do this, you need the formula for the geometric angle, which is going to show up in your in the notes that I created. It should also be in your notes somewhere. So it's arc cosine of v1 dot product v2 over magnitude of v1 times the magnitude of v2. So in order to calculate what this angle is, we have to calculate these three quantities, the dot product, two magnitudes, and then we take the arc cosine of that. So let's go ahead and do this. So v1 dot product v2, well, the way that dot product works is we multiply the values across and then sum them together. So this gives us minus 3 times 2 plus 1 times 1. And so you end up with minus 6 plus 1, so you get minus 5. For magnitude of v1, we're taking the sum of the squares and then taking a square root. Right, it's just the distance formula. So in this case, it'll be 3 squared plus well, minus 3 technically, quantity squared, plus 1 squared, and then we would put a square root around all of that. Oh, weird. Let's undo that. Okay, so we take a square root after that. And so this is going to be the square root of 10. And now let's look at v2. For v2, 2 squared plus 1 squared, all in a square root. We get 4 plus 1, 5. We get root 5. Okay. Now when we plug into this expression for gamma, the geometric angle, minus 5 goes on top, and then on the bottom we have root 10 times root 5. Now notice that root 10 actually has a root 5 inside of it, so I could split this into this quantity. Okay, and then because the magnitude of v1 and the magnitude of v2 are going to be product together, the square roots are going to cancel, and you're going to be left with 5. And so this is the quantity inside arc cosine. And then you have a cancellation, right? The 5 and the 5 will cancel. So the thing you're evaluating is arc cosine of negative 1 over root 2. Okay. And I mean, at this point, I guess maybe you could plug it into a calculator to get that value. That it would be hard to tell, I guess, otherwise. But if we reason through this, right, so this value, minus 1 over root 2, you should recognize it as the value root 2 over 2. That's just rationalizing the numerator. If you rationalize, or sorry, the denominator. If you rationalize the denominator, you end up with this value, and that value should look really familiar to you, right? So you, when you think about the values that cosine takes, so this is going to like the unit circle, which I guess I can pull up for those of you that don't have it memorized. So when you think about the values that cosine takes, which is going to be this row, you see that root 2 over 2 shows up for the angle pi over 4. That's a 45-degree angle. And so you should be thinking that this should be some version of a 45-degree angle, arc cosine. Like the angle that arc cosine is going to spit back is some version of a 45-degree angle. But notice they have a negative here. So this is where we factor in what is the range of the arc cosine function. And it's going to be these two quadrants that are shaded. And so we want a 45-degree angle where cosine is negative. So that's not the first quadrant. That's going to be the second quadrant. And so your actual angle is going to be this that I'm drawing in blue. So it's a 45-degree angle in the second quadrant, which in other words is 3 pi over 4. So this is the value that you should get. Okay. And I guess like if you didn't know that value off the top of your head, that is on the formulas or the unit circle sheet here. So 45-degree angle in the second quadrant. That's the name of it there. Okay. Next problem. So find all solutions to this trig equation. Tangent of something, of some quantity is minus 1. The first thing we want to do is we want to, um, weird, abstract out that angle. So let's just replace all of this with theta, okay? So then what we're thinking about first is what values theta are going to solve this simplified trig equation. So you should think through your values for tangent. If you need the unit circle, you can look at that. And so you think, okay, when does the function tangent take the value 1? Well, in terms of the special angles, you see that it takes the value at pi over 4. So the angle that we are after is pi over 4, but in the quadrants that make it negative 1 rather than positive 1. Okay. So one way that I've phrased this in recitation is that what we found is that the reference angle is a 45-degree angle, but we don't know what quadrants theta actually are. When you do a trig evaluation on a reference angle, that's going to be plus or minus that function on just the angle in general. This is how reference angles, and that's why reference angles are useful. So the two angles that we are after are going to be these two guys, because these two quadrants, the second and fourth quadrant, are where tangent takes on negative values. And if I want to mark where the reference angle shows up, it's actually over in these two places. But you know, the actual angle that is being displayed here is this one and this large one. Those are the actual angles that these points correspond to on the unit circle. Okay, now let's give names to these angles. So 3 pi over 4 and 7, 1357, yeah, 7 pi over 4 would be names for these angles. You can see that over here with 3 pi and 7 pi over 4 for the second and fourth quadrants. And now, so these names for these angles are, they're the names in the first revolution about the unit circle. We want to find all solutions, which means that we want to tack on multiple revolutions of the unit circle. So we tack on plus 2 pi k to all of this. Oh, actually, yeah. Well, we will have that, but there's one more step after that, right? So notice that we are only solving the sub problem so far. Plus 2 pi k, and also 7 pi over 4 plus 2 pi k. So these would be solutions to the equation. Maybe I'll try to, if I were to box it. Oh, so these are solutions to that, right? Maybe I'll point to it. So that solves that, but that's not the original problem. The original problem has the theta actually be this quantity, 3x plus pi over 4. So now we bring back x into our problem, okay? So we had assigned theta equals this expression. Now let's substitute it back in at this point. So 3x plus pi over 4 is equal to 3 pi over 4 plus 2 pi k, and also we can use the other set of solutions, 7 pi, theta equals, sorry, I should replace the theta equals first, 3x plus pi over 4 is equal to 7 pi over 4 plus 2 pi k. So we have these two equations that we now solve for x, because our answer should be in terms of x. Okay, so we go ahead and we manipulate this. It's just a little bit of arithmetic. So 3x, we have 3 pi over 4 minus pi over 4. That gives us 2 pi over 4, which reduces to pi over 2. and then the plus 2 pi k doesn't change. But then finally we have to divide by 3. So we get x equals pi over 6 plus 2 pi over 3k for our for solutions corresponding to the first equation. Now for the second equation, 7 pi over 4 minus pi over 4, that's going to be 6 pi over 4. I'll just write the 3x first. So 6 pi over 4, but there's a 2 in common, so that becomes 3 pi over 2. Right, simplifies to that. And then plus 2 pi k, and now we divide by 3. So when we divide by 3, the 3 on top will cancel. You get pi over 2 plus, and then again, 2 pi over 3, k. Right, my computer is, I need to pause. Okay, and then the next thing, or, well, to wrap up this problem, I should also then specify what k is. K kind of just appeared out of nowhere, so we'll just put off to the side where k is an integer. Okay, so this is the full set of solutions. And, well, okay, I'll say one additional thing about this. So if you were a bit clever, you would have actually also, you would have noticed that these solutions actually can combine. Okay, so you can write your answer this way, but there's actually a simpler way to write it, and it's going to be equivalent. So whoever grades it, hopefully they will notice this. I mean, they better notice this, but yeah. So you could write it this way, or you could actually notice that if I take this point and I rotate 180 degrees, I get to this point. I rotate 180 degrees again, I get back to this point. So there's a that means that I can actually have the amount being rotated. So the other solution, or the other way to present our solution, is to solving this equation, the simplified equation. You would have theta equals 3 pi over 4, and then plus pi k, right? We have the amount of rotation that we repeat. And basically every time that k is odd, you're going to actually land in the other set of solutions. You're going to get to points that correspond to this solution. And then for even ones, you get to this point. Okay, so if you did that instead, if you noticed the symmetry, then when you calculate the rest of it out, you get 3x plus pi over 4 is equal to 3 pi over 4 plus pi k. And then solving, you would get 3x is equal to pi over 2 plus pi k, and so you would get x is equal to pi over 6 plus pi over 3k, where k is an integer. So this is another way to present the answer to this problem. You can kind of see, like, it corresponds to the first guy, but you have the amount of you have the rotation, so you make it kind of twice as fast. Not really twice as fast. More like twice as slow. Anyway, that's it. So right, next problem. So for this one, we're given a sinusoidal curve. We want to read off, or we want to figure out what the equation for it should be just by looking at the graph. So first thing I'm going to do is mark the points that I'm going to consider. So I'm going to mark one whole period. We start and end right there. And then you notice that the rest of the curve is created from this packet by just copy and pasting to the left and to the right of it. Alright, so now, let's see. This would have the value 1, 2, 3, 4, 5, 6, 7, 8, 9. So this would be 9. And then the height, 1, 2, 3, 4, is there. Okay. So, amplitude is the height of the sinusoidal curve. So we know that that's 4. To calculate the period, well, let's also just maybe reference the notes that I have. Where did I put it? Sinusoidal to equation. So, in order to do this, we're going to need So period is start minus end, and I abbreviate it with P. Phase shift is going to matter for the part B of this problem. So a period is going to be 9 minus, oops, oh, it's doing something again. Period is going to be 9 minus 1, which is 8. Okay, so these are the two values that we want. I don't know, I'll just circle them. Okay. For coefficients A, B, and C, well, we can write A down immediately. A is the same value as we've figured out before. It corresponds to amplitude. For B, we need the formulas. So for B, it's 2 pi over P. And C is negative phi times B. Just, again, from the formula sheet. Or note sheet. Okay, so now 2 pi over P. P is what we calculated before, so let's just plug it in and simplify. So we get pi over 4 for our B. And for our C, we would get negative phi. Now, phi is what? In the way that I've marked this, the window that I'm considering, or I guess you might call it the fundamental domain, it's this portion of the graph from 1 to 9, x equals 1 to x equals 9. And so, phi in this case is 1. Phi is the starting value. So 1 and then times b. Well, b is what we computed above right here. So then what we get for c is minus pi over 4. And there we go. We can now circle these three values. So that answers part B. Okay. Next, number 4. Find all solutions to this trig equation. Right. So we've done problems like this in the homework. When you see something like this, with the fact that it has a cosine squared and a cosine, it should make you think that to treat this as a polynomial. So we'll treat this as a polynomial by letting y be cosine of x. And then we do this variable substitution. We just replace this out. We get 2y squared plus 5y minus 3 equals 0. And then we try to factor this guy. Or you could use quadratic formula if you're more comfortable with that. But one thing I've noticed is that some people don't know how to use quadratic formula. So that was an interesting bunch of mistakes that I saw. But, I mean, either way, you factor this guy, and you get solutions to this quadratic, and then you have to bring it back to cosine. Let me just factor this guy. So 2y and y. That's the only way to factor this 2y squared in the front. And then we think about this minus 3. Okay, well, we think about 3. The only way to factor 3 is 3 times 1. So 3 has to go in one of these places, and 1 has to go in the other place. And we notice we want to somehow make things match up to equal 5. Okay, so, and there's a minus here, which means the signs are going to be opposite. Well, the only way to make this work is if I do 6 minus 1. So I need 6 here, and I need to make 1. So notice that when I do calculate the middle term, I do 3 times 2y, giving me 6, and then minus 1 times y, giving me 6 minus 1, giving me 5y. So I got the middle term, and I can check that I got the last term as well. Yeah, so this is how you factor this quadratic. And I saw plenty of people not factor things correctly. Yeah. Okay, well, so if you get that, then the next thing to do is to substitute back the cosine. So y, we had set y equals cosine of x. Now we bring the x back. So we get 2 cosine x minus 1 equals 0. And we get that cosine of x plus 3 equals 0. All right, well, let's do this case first, because we know we can kind of spot it right away, right? So if we just solve for the trig part, we see that this equation being holding true would require that cosine of x squared to equal minus 3. Well, that's impossible. And I mentioned why probably in the practice video, and also recitation, but I'll say it again. The fact of the matter is that both sine and cosine are bounded. between -1 and 1. You can think about the graph of these functions, and you'll notice that they never, so this is the graph for sine. If I wanted to make it cosine, I'd have to start at 1 here and then go up. Oops. What's going on? I'd have to start at 1 and then do the whole wavy part. All right. But the key thing about the graph is that it's always between the lines y equals 1 and y equals -1. It never exceeds that. So yeah, having cosine of x equal -3, it's not possible. So this side contributes no solutions to the original problem. Now we try the other side. So with the other side, we solve for the cosine x, and so that means we add 1, divide by 2, and then we get this equation. Cosine x equals a half. Now this requires us to have our unit circle knowledge. When is it possible for cosine of x to equal a half? Well, the first angle that should come to mind is the 60-degree angle, pi over 3, right? Does the problem specify in radians? So it does say to do it in radians. Okay, so you should use pi over 3, but you can think about it as 60 degrees in your head if you want, if you prefer. Okay. And yeah, I'll bring up the unit circle for those that aren't come through all this stuff. So we're talking about the value for which cosine equals a half. So cosine equals a half, according to this table, at pi over 3 radians. Okay, and then the other thing is, well, so that gave us one solution. That gave us the solution that looks like this. But you should know that cosine has another solution for this. It's going to be in one of the other quadrants. And so let's label our axes, sine and cosine, in the correct manner. It's kind of funny that it's x. I don't really want to have x there. It kind of is a bit confusing. But see, the x-axis corresponds to the cosine, and the y-axis corresponds to sine. So to say that cosine equals a half is to say that the x-coordinate on the unit circle equals a half. So there's only one other place on the unit circle that happens. It'll be here. Oh, it'll be here. And we know that whatever this angle is, it's going to have the same reference angle. It's going to have the reference angle that is 60 degrees, or pi over 3. So we're asking now, what is the 60-degree angle in the fourth quadrant? Well, it's going to be 5 pi over 3. And so 5 pi over 3. All right. So that's one way to write the answer. There's actually another way to write the answer. So you could instead just think, oh, if I'm flipping this about the x-axis, it's a reflection. So I can actually just, or you can think about it as rotating in the opposite direction. So first we were rotating it this way. Well, now we rotate it that way. The same amount, but just in the opposite direction. So the other way we could name this angle, maybe I'll just put it right next to it. We could name it 5 pi over 3, like we did before. But we could also name it minus pi over 3. And then this guy I'm going to also label there. Okay, so we have the names for these two angles. Are we done yet? Well, no. We need to find all solutions to the equation. What I've written now, just now, these are only the solutions in the first pass around the unit circle. So to then bring it all, to bring all of the solutions into our answer, what we need to do is tack on a plus 2 pi k. So let me just then, I guess I'll put it down here. X is equal to, right, so now there's two different ways you can do it. So if you didn't notice that 5 pi over 3 is equivalent to minus pi over 3, you would have written it like this. You would have written it 3 pi plus 2 pi k, and also 5 pi over 3 plus 2 pi k, where k is an integer. That's one way to write it. However, if you actually notice that 5 pi over 3 is equivalently expressed as minus pi over 3, you could actually just kind of, it's almost like you're collapsing it, but not quite. You just, you hide the other guy in the minus portion. So it's plus or minus pi over 3. plus 2 pi k. Again, k is an integer. So you can write it like that as well. So these are two different ways of presenting our answer. All right. My encoding is overloaded. That's not good. I really hope. Okay. Right. 5. Let's see, how many pages are there? Okay, there's only 2 more pages. Right, so this one, rewriting this trig function into standard form. So let's first, the first thing that I would want to do to this guy is to rewrite it in kind of the better order. So notice that the problem is sort of being a little tricky. It puts the x part at the end, which I don't like. So I want to see it like this. Okay, because the thing is that you have a equaling 3 and b equaling -2. Right. C is the pi over 4, but we don't need that for putting things into standard form. So we have these two guys. Well, notice that A is positive, B is negative. So coming to the notes on how this works, that falls under the case where just B is negative. Okay, and the notes tell us that we should use this formula to convert our trig function. So sine of pi. So we want to use sine of or theta is equal to sine of pi minus theta. We use this guy to convert the given trig function into standard form. Okay, so now let's go ahead and try this out. So I'm going to copy down the original function first, and now let's apply it. So what this is saying is we can replace our angle, but we'll keep the stuff in front the same. So 3 sticks around. We still have sine. But now this guy we can negate. So we have pi minus and then theta. So this was our original guy, theta. We will minus that whole thing. So we end up with this expression. And let's go ahead and simplify this. Distribute the negative, do the subtraction. So you get 3 pi over 4 plus 2x. Okay. I would have preferred actually to have used this guy that I converted, but it's fine. 2x plus 3 pi over 4. Just get it into really the standard form. Perhaps I will box that. Okay. Right, so from that, can we read off the values? Well, for amplitude, we know it's 3. Amplitude is the number in front. For the period and the phase shift, there are formulas for those. So let's see. Standard form to hand sketch, that's what these are. So period is 2 pi over b, and phase shift is minus c over b. So this guy is 2 pi over b, this is minus c over b. And b is the 2. So we get 2 pi over 2, which gives me pi. And then the minus c pi over b gives me minus 3 pi over 4. And then all over the b, which is 2. Well, the denominators, you can think about that in a couple different ways, but this is going to become minus 3 pi over 8. Okay. So we got our amplitude, our period, and our phase shift. Maybe I'll circle these. All right, now sketch the graph over 2 periods. So let's mark out 2 periods. Oh, actually, I can just use this guy. Make a straight line. All right, and now let's mark off 2 periods. So we will start here, and then we'll go here, and then we'll go here, and then we're done. All right, so I'm going to fill in these intervals, these 2 intervals, with the sine curve. Heck, I could even do it now. Let's do it now. Well, that's kind of lopsided. That's better. Okay. And let's see, what are the values? Well, this is where I start, so I want that to be my phase shift, which is what we calculated here, minus 3 pi over 8. Now to go from this part to this part, I end up going the length of an entire period. So I end up adding pi to that. Let's do the calculations off to this side. So we start at our phase, and then we add on our period, which is pi. That gives me 5 pi over 8. And now we add on another period in order to get the value for this last tick mark. So that will give me 8 plus 5 is 13 pi over 8. So the values are 5 pi over 8 and 13 pi over 8. Okay. And now the next thing to do is put the y-axis where it should be. So it's going to be around here, let's say. We know it's closer to the minus 3 than to the 5. And we should also then mark off the values for the amplitude. So this will be 3, this will be minus 3. And there we go. That is our sketch. Okay. For number 6, we have to find the dot product. We're given 3 different norms, 3 different magnitudes. So we've seen this type of problem in the practice exam. We know that we're supposed to use the generalized Pythagorean formula, which says, well, if you don't have it memorized, you'll find it in the thing I typeset somewhere. Where did I put it? There. Yeah. But it really does behave like the Pythagorean theorem. At least the first 3 bits do, and then the rest is like to deal with the angle. So it's like a correction for the angle. So like this is your c squared basically equals a squared plus b squared, basically is what this is saying. But then we have a correction because our angle isn't necessarily a right angle. So then we have this 2 times v times v, v1 times v2. Yeah, that's what the formula says. Okay. Okay, and then how do we compute this thing? What are we after? We're after the dot product. We have all the other quantities, so we may as well just plug things in right here. So 6 squared, 3 squared, plus 5 squared equals, minus 2, and then v1 times v2, which is the thing we're after. So now we move things around. Let's square the 6, we get 36. Minus 9, minus 25, and then we have to divide by negative 2. And that will solve for us the quantity we're after, v1 dot v2. Alright, so then doing the subtraction, it's going to be 2. So you get 2 over minus 2, which is equal to minus 1, which is equal to v1 dot product v2. So I'm going to box it like that. Okay. Number 7. Solve this trig equation over this interval. Okay. First, we should think about when does sine take the value root 3 over 2. So this is a unit circle thing. Let's look at our unit circle. And for me, I like this, the actual table values. So we see that sine takes the value root 3 over 2 for angles that are pi over 3, for 60-degree angles. Okay, so we're talking about a 60-degree angle, but in quadrants where sine is negative, because of this negative that you see there. So when is sine negative? Well, let's draw our axes, unit circle, just imagine the circle. So then, well, sine is going to be negative on these bottom 2 quadrants, quadrant 3 and 4. So we're talking about 60-degree angles in quadrants 3 and 4. Meaning that is a 60, and that is a 60. That's how we draw the reference angles. Okay, so now these angles, what are the names for these angles? Well, this is where we would think back to our unit circle. 60-degree angles in the third and fourth quadrants. They're given right there. I give you the names right there. So 4 pi over 3 and 5 pi over 3. Those are the names of those angles on the unit circle. Okay, right. Well, now we need these would be the names of these angles in the standard, I guess, interval that we're used to, 0 to 2 pi. But we actually want it over this larger interval. So let's try to now, I guess, wrap around the unit circle multiple times. In order to do that, what I'm going to want to do is to convert some of the values. So the 2 pi over 3, I want it to have the same denominator as the angle I'm working with. So I'm going to think of this 2 pi as 6 pi over 3. And then the minus 3 pi, I'm going to think of it as minus 9 pi over 3. This is just to make comparing the values that we get out, making the comparison a lot easier for us. And then what we do is we're tacking on a plus 2 pi k, so I'm going to think of this as we're tacking on a 6 pi over plus or minus. We're tacking on plus or minus 6 pi over 3. So we just adjust our numerator by adding or subtracting multiples of 6. Okay, so we're going to want to start with 4 pi over 3, the original guy. And now if we try to go up, we would end up with, well, 10 pi over 3. But notice that 10 has exceeded the 6, so that is not one of our answers. If we go down, we subtract 6, so that's going to give us minus 2 pi over 3. If we subtract down again, we get, minus 8 pi over 3. And notice we're still inside of our interval, right? We're still inside the interval. We're still not lower than negative 9. We're still above negative 9. But once we go one more time, then we end up below negative 9. So actually, it's just these three values that correspond to this family, the family of like 4 pi over 3. So unfortunately, I decorated it quite a lot. So let me just maybe I'll circle the values that we actually found that work. And then, so those were the angles that are equivalent to this, the 4 pi over 3. We also need to find the ones that are equivalent to 5 pi over 3, that live within this interval. So let's do that. 5 pi over 3. If I try to go above, I would add the 6 again, and we would get 11 pi over 3. And notice that that's outside of our interval, our window, so we can get rid of that. Next, we subtract 6, so we get minus pi, minus 1. We subtract again, we get minus 7. Subtract again, we have left the minus 9. So we just have these three solutions. I'll just circle all three of them. So the answer for this problem is those 6 values. Okay. All right. And this is the last problem. There's 2 parts. Okay. So notice that one is arc trig of a trig, one is trig of an arc trig. So we have those 2 different situations happening. The first one is the one where you evaluate, or where you can evaluate the inner function. So let's see. Well, how would I spell this out? We know that the 7 pi over 6 is a 30-degree angle. So we need to think, well, what kind of value does cosine take on a 30-degree angle? 30-degree angle is this guy. So it's going to be root 3 over 2 plus or minus. Root 3 over 2, but is it a plus or a minus? Well, let's think about cosine, sine. 7 pi over 6, what quadrant did that land in? 7 pi over 6 landed us in the 3rd quadrant. So we know it's actually the 30-degree angle in the third quadrant. We don't need the third degree right now. But I'll draw it anyway. So yeah, so it's this guy. And that tells us that cosine is actually negative in this quadrant. So I can put negative there. So now we've evaluated cosine of 7 pi over 6. Now we wrap an arc cosine around this. Okay. And let's think about arc cosine. So, well, what's going to happen is that the reference angle is the same. So we know that the theta ref, right? Theta is 7 pi over 6. Theta ref is pi over 6. It's a 30-degree angle. So it's going to be some 30-degree angle, but it's actually not going to be in the same quadrant, because you should remember that arc cosine has outputs in the first and second. So if I use the same diagram, arc cosine actually outputs only in these two quadrants. It's not going to, is that the way to phrase it? Yeah, so it doesn't give me back my original angle, is what I'm trying to say. So it's going to be a 30-degree angle, but not in the third quadrant anymore. Well, so which of these quadrants is it going to be? Well, this value is negative. So it's going to be, it can't be in the first quadrant, because the first quadrant, everything is positive. So our angle is actually this guy, a 30-degree angle in the second quadrant, which gives me the value 5 pi over 6, which you can see from the unit circle. So a 30-degree angle, but in the second quadrant instead, is 5 pi over 6. And may as well box that. Okay. Now for part B, we have trig of arc trig. The arc trig, the way we handle this is we know that it's, whatever this is, it's going to output some angle. This is going to give me some angle. So I should view an arc trig evaluation as corresponding to some triangle. And let's think about where this arc tangent is going to live. Which quadrant is it going to be in? So notice that it's a negative, so it's not the first quadrant. So we think, okay, what is the other quadrant that arc tangent sends things to? It's going to be in the fourth quadrant. So we know it's going to be that the angle that arctan is going to return for us, it's going to be an angle in the fourth quadrant. It's going to look something like this. Let's draw a triangle, and let's think about how tangent is going to work. So tangent is opposite over adjacent. So we are going to put 1 and 7 to kind of split our fraction up. And now let's see. We want to put the negative where it makes sense. So that's going to be on this side, because this side can be viewed negatively since the y-coordinate is negative here, whereas the x-coordinate is positive. Okay, and the last ingredient I'm going to need is the hypotenuse, the length of the hypotenuse. So 49 plus 1, I square both sides, 49 plus 1, 50. So I have root 50 on the hypotenuse as the length of the hypotenuse. Okay. Now, and I should also just label my angle theta. There we go. Okay. Lastly, what is cosine of this triangle? Cosine of theta, where theta is given by this triangle. So cosine is adjacent over hypotenuse, so we get 7 over root 50. And there we go. That's the answer to that. Now, there is one thing I'll say. So this one actually, if you did it the formulaic way, you're going to get an answer that looks quite different, but it's actually the same. And we may as well go ahead and show that that's the same, just so that people won't be wondering too much about that. So cosine of arctan, by the formula, it's going to be 1 over root 1 plus x squared. So I'll just copy down that formula. So cosine of arctangent of x is 1 over root 1 plus x squared by the formula. Good, I got it down correctly. So now if I use that formula, well, what that's going to say is that when I plug minus 7 into that, probably should copy the rest of this, arctan 1 over root 1 plus, well, negative 1 over 7, you kind of know that the negative is going to get squared away. Well, let's try to maybe take it step by step. So negative 1 over 7 is quantity is going to be squared. Then you take a whole square root around that, all that. Okay, well, these two expressions look very different. So I'm going to go ahead and show you that they are actually the same. The first thing we want to do is we want to get rid of that square. Okay. So when I square this fraction, the negative disappears and the denominator squares. The numerator squares as well, but 1 squared is 1. So we get this. Okay. Next, I want to combine this. I want to actually do this addition, because then I can think about the square root. So if I do this addition, I need a common denominator, which is 49, and then I add the 1. So we get 50 over 49 when we do the addition. Now I'm going to take the square root. Okay, so and I will, the way I'll do this is I'm going to split the square root over numerator and denominator. Right, the square root actually splits over multiplication and division. So we have this. And then the square root of 49, of course I know what that is. So this is, make this the big guy, over 7. And then lastly, I want to actually get rid of this fraction in a fraction. And the way this works is, think of this as 1 divided by a number. So that's, you can reciprocate that. This is going to be 7 over 50. So we indeed end up at the same answer as we would get if we thought of things geometrically instead of algebraically. Okay, and well, I guess that's it.